let's start. Okay, let's start. So I'm very happy to announce our today's speaker, Alexander Soibelman from IHES. And the title is Quantized Integrable Systems, Normal Forms and Variations of Hodge Structure. So please. Yes.
So thank you. Yeah, can everybody hear, or am I audible? I haven't actually tested my microphone.
Yes. At least I hear you. Okay.
That's great. That's great. Okay, thank you. So thank you for giving me the opportunity to give a talk. And what I'm going to be talking about today is basically an ongoing joint project with Maxim Kontsevich. So I want to start out by giving some motivations for this work, and start out with something very basic. So I want to start off with talking about the complex Morse lemma. So just sort of remind everyone, if you have this kind of complex function, a homework function, with a non-degenerate critical point, let's say at 0, so function from Cn to C, non-degenerate critical point, meaning that the derivative is 0, but the second derivative, or the matrix of second derivatives, is going to be non-singular. And so then you have the complex Morse lemma, which basically
F is equal to F0 on your slide. Is it a typo? Yeah.
This is the derivative. There should be parentheses around the df, but it's the
value
derivative
of
at 0.
Okay, thank you.
So so then the just complex Morse lemma means that, or says that you can choose. You have a local choice of coordinates that turns the function into the sum of squares. So in this case, for the Morse lemma, the choice of coordinates, or the change of coordinates, is this local holomorphic isomorphism. But you might ask the question of what would happen if instead of that, you were to only allow local symplectomorphisms to be used. And so there is an answer to this question. And just to set it up, I'm going to have function h that's now going to be going from C to the 2n to C. And once again, it's going to have a non-degenerate critical point at 0, and the value of the function at 0 is 0. So now C has this symplectic form, which in these coordinates, where pi and qi is just going to be written like this. And so there's this classical result due to Birkhoff that essentially tells you that you can do a formal coordinate change, formal symplectic coordinate change, that will also allow you to write the function down in a certain form, or certain normal form. So this is what's happening next. So again, based on what I said in the previous slide, the setup is that we're looking at a function h with a non-degenerate critical point at 0. So you can write it down as a power series in terms of something that begins with a quadratic term and then has some higher order terms after that. And so this is going to be an element of this Poisson algebra of formal power series in pi and qi, where I goes from 1 to n. And this quadratic part is going to be this h2. So this Birkhoff normal form theorem just says that if you can bring the quadratic part of this formal germ of h to a specific form, namely you can get it to be this linear combination of sums of squares of the pi and qi, such that these coefficients are linearly independent over q, then there's going to be a Poisson automorphism. So this ring of formal power series is a Poisson algebra, where the Poisson bracket is coming from the standard symplectic form. And so there's going to be a Poisson automorphism that changes the function h into its Birkhoff normal form, which is again going to be some sort of formal power series written in terms of these sums of squares. And of course, it starts off with just the linear combination that is h naught. So That's essentially the Birkhoff normal form, and this condition, this additional condition that I require for these AIs to be linearly independent is called non-residence. So this is the classical picture, but you can also quantize this and look at a quantum picture. So this is called the quantum Birkhoff normal form appropriately. And the idea is now I'm going to be replacing the algebra of formal power series and 2n variables with a non-commutative algebra of formal power series, but now they're non-commutative in the variables qi hat and pi hat. And it's also going to be, there's another variable that commutes with these, which is this h bar, this Planck constant. And so this is just going to be formal power series in h bar, where the coefficients are these non-commutative formal power series in qi hat, pi hat, and there's just the commutation relations that are just telling you that the pi hat and the q j hat commute in sort of this this nice way that is the same as you would you would have for just qi and the partial derivative with respect to qi. So,
excuse me, a square root of -1, does it have any meaning, or it just for some, I don't know, because you like to please physicists?
it's basically just to please a physicist to get the quantum harmonic oscillator to be the pi squared plus qi squared.
Which means that there is no antilinear involution or something, yeah. no Hilbert's. Okay.
Right. So the quantum Birkhoff normal form is just sort of this quantum analog of the formal Birkhoff normal form that I talked about previously. So now HQ is going to be an element of this algebra of these non-commutative power series, and you can take its semi-classical limit as h bar goes to 0, meaning that I'm going to be taking its image in the quotient by the ideal generated by h bar. So when you take AQ quotient out by this ideal generated by h bar, you just get the standard formal power series in 2n variables. And I want the image of HQ to satisfy the conditions for that H does for the Birkhoff normal form in the classical case, meaning that, again, I want the image to have sort of a Morse critical point at 0 and the value at 0 to be 0. So sort of these kind of things, and this non-residence condition in addition to that. And so given all of that is true, then there is an isomorphism of this quantum algebra of AQ, or monomorphism, and it takes HQ to its quantum Birkhoff normal form, which is now going to be a formal power series in n variables as before, but now there's an additional variable h bar. So it's a formal power series in h bar with coefficients in formal power series of the TIs. And so the Birkhoff normal form is just going to be.
Yeah, is it a theorem? it's kind of, you highlighted it. Is it a theorem?
It's a theorem. I'm not sure what the correct attribution is, or who is the first person to prove it. I've seen it in several different places, but yes, it's a theorem. Yeah, so you can transform HQ into its quantum Birkhoff normal form, which is again going to be this power series dependent on now these sort of quantum sums of squares. So it's going to be pi hat squared plus qi hat squared instead of pi squared plus qi squared. And so sort of if you think about these in terms of the differentiation of q as pi hat, a sort of differentiation, a partial derivative with respect to qi, then you sort of get the quantum harmonic oscillator.
So when you write FQ, I understand it's just an ordinary series of commutative commuting variables. Yeah, so
Yes.
then you kind of silently mean that these HQI commute with
Yes.
each other. Yeah.
Yeah.
Okay.
So the
Okay.
I didn't say this, but the HQI do commute with in this algebra, and if you look back on the previous page, the HIs here Poisson commute. So
okay.
yeah, that's going to come up later. Right. So this is this FQ is called the quantum Birkhoff normal form of HQ, and again, both in this case and in the classical case, this normal form is unique up to psi. So now, again, I want to continue or sort of conclude with this motivating part of this talk, and to do so, I want to talk about how this applies to computing eigenvalues, computing spectra of quantum Hamiltonians. So everything that I've done before here is just sort of algebraic or some commutative, not commutative algebra. So you can try to apply this to actually compute spectra of differential operators acting in a Hilbert space. And so the idea is if you have a polynomial differential operator, you can think of it as an element of this algebra AQ, and you can bring it to its quantum Birkhoff normal form. And the something I didn't say in the previous slide, but the automorphisms of this algebra that are used to bring it to this quantum Birkhoff normal form are inner automorphisms. So it's kind of conjugation with an element. Meaning that if you think about this thing as a differential operator and you think about trying to compute its eigenvalues, then the eigenvalues of the normal form are going to be the same as the ones for the starting operator. So because the normal form is computed in terms of these sums of squares, you can use the eigenvalues or the spectrum of the sum of squares or the quantum harmonic oscillator and plug it into FQ to get the actual answer for spectrum of HQ. So this is exactly what Sjostrom did, or Sjostrom proved in 1992. So there's essentially this theorem that if you have the Schrödinger operator that's acting on actual Hilbert space of L2 functions on R to the n, then given some sufficiently nice conditions on this V, namely that you actually want there to be a non-degenerate critical point, and you want that to be the only critical point, as well as some other conditions, then you can get the asymptotic expansion for the eigenvalues of this HQ just by plugging in the eigenvalues of the quantum harmonic oscillator into the quantum Birkhoff normal form. And so, yes.
I kind of am looking at this theorem. So V is V a polynomial? Or...
Yeah, V is a polynomial.
All right. So then indeed HQ, you can associate to it an element of this algebra. Okay. And these conditions, they are some analytic conditions. So just V is a polynomial and this is it.
I mean, there's the condition that there's just one critical point and that it's not degenerate, but there's also other things.
All right. Mm-hmm.
Yeah. So from now on, I'm essentially going to be, this is going to be the motivation, but from now on, I'm essentially just going to be explaining different geometric interpretations for the quantum Birkhoff normal form. This is, so just start off with, I talked about this algebra AQ of these formal power series in H bar with coefficients and some non-commutative formal power series. Essentially, you can think of this as a formal germ of deformation quantization of c to the 2n. So if you have your algebra of holomorphic functions on c to the 2n, then there's this standard quantization of the functions in terms of this Mayal star product, which the first two terms is given over here, but yeah, essentially it's a non-commutative product on the algebra functions, and it somehow remembers both the commutative product and also the Poisson bracket. So that's what this stir product is doing, and the idea is to try to use this interpretation in terms of deformation quantization to sort of introduce more geometry into finding the Birkhoff or the quantum Birkhoff normal form. So the second observation that I want to make is something that I've again mentioned a little bit earlier, and that is that if you're looking at the classical Birkhoff normal form of a function or of a Hamiltonian, then that's going to be Poisson commuting with the sums of squares that it's expressed in terms of, and the sums of squares also Poisson commute with each other. So this sort of suggests that maybe the correct geometric setting for both the Birkhoff normal form and the quantum Birkhoff normal form is going to be something dealing with integrable systems, since that also involves finding finding the right number of Poisson commuting functions. So this is now sort of going on. I want to talk about what I mean by integrable system. So to understand the quantum Birkhoff normal form, I want to quantize integrable systems, but since I'm using slightly non-standard terminology, then let me just sort of say what I mean. And by integral system, I mean that there's going to be a surjective mapping going from a complex symplectic manifold to just a complex manifold, and the generic fiber is Lagrangian. So I don't require fibers to be tori or in fact to be compact. So, again, this is sort of standard terminology, but because
so this is
yes.
basically just a Lagrangian fibration.
Yeah.
Okay.
Yeah.
But not necessarily torus Lagrangian fibration, as some people in mirror symmetry get used to. Okay.
Yeah. Yeah. So yeah. So just because pi might have some critical points, I'm going to be designating by x naught to be sort of the locus where it's actually points where it's actually submersion, and then the corresponding image in the base is going to be b naught. So notice again, if you sort of give b the trivial Poisson structure, meaning the bracket of two functions is 0, then the morphism pi, or the mapping pi, is going to be a Poisson mapping. So you can look at this integral system as sort of an embedding of the sheaf of functions in the base into functions on the total space as a sheaf of Poisson commutative subalgebras. And this is in fact the interpretation that I'm going to be quantizing. So, and equivalently, you can sort of choose local coordinates on the base, and the pullback or the pullbacks of these local coordinates are going to be these pairwise Poisson commuting functions. So, standard example that's going to be important later on. It's x is c to 2n, b is c to the n, and the mapping is just going to be composed of sums of squares. So in this case, I'm going to be changing notation throughout the rest of the talk. So I'm going to introduce it now. Just going to do a change of variables. And instead of using sums of squares, I'm just going to be using products. So instead of pi squared plus qi squared, I'm just going to have xi times yi. And that's going to be defining the mapping pi. So using this interpretation, integrable systems, you can restate the quantum, or not the quantum, the Birkhoff normal form theorem in a different way. So this is just essentially reinterpreting the previously stated theorem in another way. And again, the conditions are the same as before. So you have holomorphic function that's going to have a non-degenerate critical point, and X is symplectic manifold. And so then again, just assume that the value of the function at the non-degenerate critical point is 0, and that there's this non-residence condition satisfied for the formal germ of the function. So then the following is true. So first thing is that there is actually going to be this kind of injective morphism of Poisson algebras, where the formal power series of a trivial Poisson structure, and then the formal germ or the germs of formal germs of functions near x naught on x just has the sort of inherited Poisson structure. And then the first part of it is just that the image contains the formal germ of H. Or in other words, sort of a more, maybe a more intuitive way of saying it is that you can take H and complete it to an integrable system, meaning that you can find enough Poisson commuting Hamiltonians or Poisson commuting functions, and then that's going to give you a germ of an integrable system.
Enough means n-1?
It's either n-1 if you include H, or n if you don't include H, and it's just going to be some sort of power series in the n that you do find. So yeah,
I'm confused. Just power series?
Yeah,
just
everything is just
for
for formal power series. Yeah.
Okay.
Yeah. So basically, that this first part says is that there's going to be a formal germ of an integrable system, and H is somehow sitting inside it. Right, and so the second part of this is the part that's actually referring to the Birkhoff normal form, and that is you can write down this kind of commutative diagram where the vertical arrow on the left is sort of the embedding, and the vertical arrow on the right is just going to be the thing you get from the example that I showed previously. It's just going to be sort of the formal germ of the integrable system described on the previous slide and example with the sum of squares. And so you get a commutative diagram, and the important thing is that this morphism at the top is essentially going to be the thing that's transforming the formal germ H into its Birkhoff normal form. So then this is
so this is just a restatement of
yes,
of
this is just a restatement.
Okay.
Yeah, this is just a restatement of the Birkhoff normal form theorem. Yeah.
Okay.
So and the idea is that stated in such a way, it can also quantize this, all these diagrams, or rather this diagram and both of these statements, and obtain a similar result or similar reinterpretation of the quantum Birkhoff normal form, but now we have things involving deformation quantization. So and in order to do this, you want to be able to quantize the notion of an integrable system. So this is what's next. And so here the idea is that, well, you can interpret the integrable system in the way that I've stated as an embedding or of functions in the base as a Poisson commutative subalgebra into functions in the total space. Well, and now you replace functions on the total space with their quantization, and then you want the embedding to be commutative instead of Poisson commutative. So you have an integrable system defined by pi, and the quantization is just going to be a quantization of functions on the total space. And this is sort of this quantum sheaf of functions. So you have a sheaf of associative algebras over formal power series in H bar. And if you mod out by the ideal generated by H, you just get back the functions. But also you have the sheaf is locally isomorphic to deformation quantization sheaf, meaning that you're just looking at formal power series in H bar with coefficients in holomorphic functions. But instead of you having the usual product, you have a non-commutative product, which is the star product. And so the star product is some kind of non-commutative deformation of the normal product. So it's going to start off with a normal product, and then the higher order corrections are given in terms of bidifferential operators. And so then this is deforming the multiplication. And also there's a second condition which says that this star product also remembers the Poisson bracket. So that means you can recover the Poisson bracket by taking the commutator, dividing it by H, and then getting rid of all of the higher order corrections in H bar. So this is a quantization of functions on the total space, and then to quantize or finish quantizing the integral system, I just need to have this morphism that embeds functions on the base into quantum functions on the total space, which is the second part. So
is it automatic that modulo H bar you have this n commuting Hamiltonians locally?
Yes, I think so. Yeah.
Because where this Lagrangian condition is hidden.
Yeah, I mean, I think so. I think it's automatic. When you mod out IH bar, then you just get the old morphism with the function of the base being embedded in functions in the total space, and then the condition of the Lagrangian condition is in that, because you get that it's a Poisson morphism.
I mean that if your kind of fibers, it's I do not see why the dimension of the base should be the same as dimension of the fiber. Like if you have just a line, one function, like you have polynomial in one variable, you can embed it anywhere injectively in any, I mean, you do not need to find n-1 additional.
I mean, you don't, because there's already, that's sort of the n=1 case where it's just a surface mapping to some.
No. I mean, whereas if you have like million dimension total space and one dimensional base, where
I mean, you don't, because the dimension of the base is half the dimension of the total space.
Okay, yeah. So you assume that you are given the integrable system. Okay.
Yes.
All right.
Yeah. So this is only quantizing integral systems. I mean, you could use a similar definition to.
No. I mean that something I do not quite understand. Where is the compatibility modulo H bar with all the structures? I understand that modulo H bar you reproduce the sheaf of algebras on X. This is true. But this embedding in the part 2, injective homomorphism, what happened? Is it automatic that modulo H bar, it gives you Poisson embedding?
I think so, yeah.
All right. Okay, good. Thank you.
Yeah. So now that there's a quantization for these integrable systems, then I want to give an example, which is sort of the counterpart of the examples for classical integrable systems that I gave before. And once again, starting off with x equals to c to the 2n and b is c to the n. Then pi is as before. It's these products, pairwise products. So it's the coordinate changed version of that previous example. And then the quantum functions on c to the 2n is going to be sort of the standard Shiva functions, or rather formal power series with coefficients in polymorphic functions on x. And the product is just the star product, the Moyal star product as given before. And then the morphism that embeds the functions in the base into the quantum functions is just going to be this kind of composition with these xi, yi's. And so if you want to try to see the picture from the beginning of the talk with these non-commutative formal power series, then you can look at the formal germ of this morphism to get that you're essentially embedding formal power series and n variables into these non-commutative formal power series in the way that that's written here, where ti goes to xi hat, yi hat.
Yeah, I ask you a question. So you take a ti which commute, all right, to the product xi hat, yi hat, which also commute, but you can you see you can make a product xi, yi and put hat over the product, which basically means that you consider a product of this function xy as an element of this quantized algebra. It seems to be different. Yeah.
I mean, if you look at the star product of just x and y, and then yeah, I mean, depending on how you write it, you get you should just get xy, something like that.
Okay. Which means that when I multiply these hats by your Moyal formula, the first element will be product xi, yi, but there will be one more term, if I understand correctly, which is constant, something like h over h bar over 2 or something. Yeah, they commute. Yeah, all right.
Yeah.
Thank you.
Right. Yeah. So the idea again is going to be I'm going to be quantizing the interpretation in terms of this commutative diagram that I had up earlier for the quantum Birkhoff normal form. So this is what's happening next. And so I essentially just am going to insert the word quantum in in the previous slide everywhere. So you have the same sort of thing. You have a quantum Hamiltonian or quantum function on the total space, and its image as sort of its semi-classical limit, its image in the quotient by the ideal generated by h bar, satisfies all of these conditions for the Birkhoff normal form theorem that I had up previously. So this x being a non-degenerate critical point, the value of the function being 0 at x naught being a non-degenerate critical point, and this non-resonance condition. And then given all of that, the sort of equivalence statement to the statement that h is part of, or formal germ of h is part of the formal germ of an integrable system is going to be this one, that you can embed these functions in formal power series rather in n variables. Well, formal power series in H with coefficients and formal power series in n variables into the sort of formal germ of the quantization at x naught, and that the image is going to contain the formal germ of this quantum Hamiltonian. And so then the corresponding condition here for this commutative diagram that gives you the quantum Birkhoff normal form is, again, so the vertical arrow here on the left is going to be this formal germ of the quantum integral system. Then the vertical arrow on the right is going to be the formal germ of the example that I gave previously. So it's this example, and this is essentially actually just the n quantum harmonic oscillator. And then the condition that it's actually turning HQ into its quantum Birkhoff normal form is given by this psi q of HQ being FQ. So this is both of this, by the way, and the classical Birkhoff normal form. These commutative diagrams are essentially telling you that the local behavior of this kind of formal germ of an integrable system, both in the classical case and the quantum case, is going to be determined by some sort of local model, and the local model is given by the two examples with the sum of squares in the quantum harmonic oscillator. So this is this quantization, and so now I want to talk about some further sort of geometric interpretations of this quantum, classical and quantum Birkhoff normal forms. And I'm going to be only discussing the n equals 1 case from now on. So in this case, the commutative diagram that I drew up for the classical Birkhoff normal form is much simpler. You just have, so this is just going to be formal power series in one variable. Those are sort of the functions of the base. And then the condition that I'm actually transforming my function h, which is also coincidentally going to be my function or my entire like integrable system, pi, into its Birkhoff normal form, is a condition that says that this bottom isomorphism that goes from formal power series in t minus b naught to formal power series in t is just going to be taking t minus b naught to the Birkhoff normal form of h. So you can think of this phi star as just the Birkhoff normal form in this one-dimensional case. So in this case, we can introduce something called the canonical coordinate. So this is essentially another geometric way of interpreting the Birkhoff normal form. So I can define it in terms of an integral over this relative two-cycle bounded by the vanishing cycle in fiber of my integrable system defined by h. So you can take the vanishing cycle near this, in a fiber near this Morse critical point, and you can sort of cover it with a film, so you get a relative two-cycle out of it, and then integrate the symplectic form over that relative two-cycle. And it turns out that in a small enough neighborhood, this thing is going to be well-defined. It's going to give you a well-defined function in a punctured neighborhood of...
So, I'm confused. Yes. Do you consider a relative cycle in a small neighborhood of a point, or it's any relative to cycle?
Yeah, it's actually just in a small neighborhood of a point, yeah.
Okay.
Yeah. So
so it is well defined because small neighborhood is a homotopy three-dimensional sphere.
Yeah.
Okay,
so it doesn't depend on the choice of relative two cycle, and you can actually integrate it to get a function. So you end up with a function that's going to be on a function neighborhood of B naught, the critical value corresponding to the non-degenerate critical point X naught. And in fact, you can extend the function to be defined at the critical value as well. So this should say at B naught, extend to B naught, not B. So now the main sort of reason why this has any relevance to the Birkhoff normal form is this following proposition that if you take phi star and you apply it to the canonical coordinate associated with pi, or with the Hamiltonian, you get the canonical coordinate associated with the product x times y. So it's with that integrable system. And because psi star is actually just taking the standard coordinate to the Birkhoff normal form, and because the canonical coordinate associated to pi naught is just the standard coordinate on the line, you end up with this relationship that essentially tells you that in order to figure out what the Birkhoff normal form is, all you have to do is express the coordinate t minus b naught in terms of the canonical coordinate, and the transition function going from one to the other is going to be what recovers the Birkhoff normal form. So that's sort of the way you can use this canonical coordinate to get the Birkhoff normal form back. And so I want to be able to do the same thing in the quantum case, but in the quantum case, there's not really any way, or at least there's not any obvious way of understanding what this integral over this relative two cycle of the symplectic form is. So in order to solve this problem, introduce a correspondence between quantum objects, which are sort of more algebraic, and formal deformations of the integrable system, which are more geometric and where you can actually compute integrals. So this is based on this idea of Garayan and Stratton, that there is a one-to-one correspondence between equivalence classes of quantizations defined in the way that I've defined them, and formal deformations of integrable systems. And here, by formal deformation, I mean I am deforming the complex structure of my manifold. I'm deforming the symplectic form, so it's going to be a formal power series in H bar, and I'm also deforming the mapping pi.
But you do not deform the base.
Yeah, but I do not deform the base. And sort of the important thing is that in order for this to actually be a correctly stated theorem, I need to throw out the critical points of pi. So this is only true if I'm looking at x naught and b naught, so pi restricted to x naught, and disregarding the critical points. And in this case, there's a one-to-one correspondence between equivalence classes of quantizations and formal deformations. Unfortunately, the quantum Birkhoff normal form lives exactly in sort of in the neighborhood, or in a formal neighborhood of these Morse or non-degenerate critical points. So you somehow have to add those back in order to connect this back up to the quantum Birkhoff normal form. So this is sort of what I want to do next. But for right now, if you sort of look at just the deformations of formal deformations of this kind of n equals 1 integrable system, then you can still define what the canonical coordinate is, just looking only at the deformations without looking at the corresponding quantizations. You can define what the canonical coordinate is near a non-degenerate critical point or non-degenerate critical value.
So your when you say like integrable system, it's just symplectic surface, maybe non-compact, actually necessary non-compact, and a function on it. That's it.
Yeah.
Okay. So
So in this case, everything simplifies. There's only the one function.
Okay.
Yeah. So here's the corresponding quantum commutative diagram that you get in this n equals 1 case for the quantum Birkhoff normal form. And once again, the bottom arrow is just going to be taking t minus b naught to the quantum Birkhoff normal form. So that's the important thing to note about this n equals 1 case. And so to sort of describe what's going to be going on the right side, the corresponding deformation, I really need to be able to write down the right deformation that corresponds to the sort of quantum harmonic oscillator. But because my correspondence only works if I throw out the critical point, I have a problem, because if you throw out the critical point, then you actually get more deformations or more quantizations than if you just left it in. If you just left it in, there's sort of one local model for quantization, which is given by the Small product. But if you throw it out, there's more. So I need to choose sort of the right deformation that corresponds to the one that comes from puncturing the quantum harmonic oscillator. And so there's this way of doing it involving gluing. So here I'm just taking my sort of classical integrable system with p naught equals x times y, and I'm throwing out the bad point at 0. And then I'm going to be gluing together my deformation, the correct deformation that corresponds to the punctured quantum harmonic oscillator out of 2 pieces. So 2 affine pieces with sort of the standard restriction, the symplectic form on them, and the gluing is accomplished via this change of coordinates on the intersection. And here, it turns out that the function that's used to actually glue these together, you can see it's this function phi, is something that's quite complicated. It's going to be this digamma function, which is the logarithmic derivative of the gamma function. And it's given as this write it down as rather complicated power series that depends on Bernoulli numbers. So this is somehow the correct punctured local model. And once you have a punctured local model, you can sort of do the same, or write down the same proposition, because now I'm able to choose the correct canonical coordinate to compare to the canonical coordinate of my deformed Hamiltonian. So I have the so this is, again, I'm missing, for whatever reason, I'm missing that there should be a phi q acting on this t canonical coordinate. So in this first line, but it's written correctly in the proposition. So you can see that in the proposition, phi q is taking the deformed canonical coordinate to the sort of standard canonical coordinate, and the standard canonical coordinate, or the standard canonical coordinate, is actually equal to the standard coordinate. So everything ends up being similar to the classical case. So once again, here it's just this argument that because phi q is taking the local coordinate t minus b naught to the Birkhoff normal form, then by writing down t minus b naught in terms of the canonical coordinate, you recover this Birkhoff normal form. So this is one geometric reinterpretation. So you can try to compute this canonical coordinate and the transition function from the standard coordinate, or rather from the canonical coordinate to the standard coordinate, to get the Birkhoff normal form and the quantum Birkhoff normal form back. But there is another geometric interpretation, which is going to be the part of this that involves variations of Hodge structure. So this sort of combines a lot of this local data into something more global. So instead of a canonical coordinate, I'm going to have a canonical one form. So the setup is now global, but it's the same as before. Everything is only in the n equals 1 case. So pi is a function going from my symplectic surface x to c, and I'm going to have some number of critical points, which are all assumed to be non-degenerate with the corresponding critical values. And so then you can write down a section of a vector bundle that's written over here. It's this essentially just the bundle that's cohomology of the fibers, or cohomology of the compactification of the fibers, since they could be non-compact, tensored by one forms in the base. And this section is just going to be given here in terms of a pairing. So if you have a one cycle, you can pair it with the homology or the cohomology part of this alpha and get a one form on the base. And you can get this by computing this kind of integral that's that you can define correctly. This is actually well defined. You can somehow integrate a two form over a one cycle in this case. And so the result of this pairing is going to be a one form on the base that is going to be called the canonical one form associated with this pi, and a fact, call it a fact or a theorem or a proposition statement, is that if you pair with the vanishing cycle near one of these critical values, then you're going to end up with a one form that's just dt canonical. So it's the one form associated with the canonical coordinate. So because the canonical coordinate is related to the Birkhoff normal form, then essentially by finding this canonical one form, you can recover the canonical coordinate up to constant. And so that means you can recover the Birkhoff normal form as well up to constant. So that's sort of another way of looking at this Birkhoff normal form.
So do I understand correctly that you have this pairing alpha and gamma for any gamma, but for the Morse critical point, you have essentially just one vanishing cycle, in your case, just one vanishing cycle sitting on your curve, and yeah. you are interested only in this pairing or what?
Yes.
Okay.
Yeah. So this is the classical case, and there's a similar sort of quantum, or rather, because everything is formal deformations, deformed case. So this vector bundle that's cohomology tensored by one forms and just kind of denoted by E, and you can do the same kind of thing. You can compute this, or you can define this kind of one form, which is now going to be a power series, or formal power series in H bar with coefficients in one forms. And you do that by this kind of pairing. So once again, you have by deformed omega, deformed symplectic form, and you can integrate it over this one cycle. And the second fact is just the counterpart of the first fact, is that once again, if you pair with a vanishing cycle, then you recover dt canonical, and because dt canonical can be used to find the quantum Birkhoff normal form, then you can find the quantum Birkhoff normal form by writing down this dt canonical, or by knowing the canonical one form. But again, you get it up to constant, which in this case means constant for all power series in h bar. So this is sort of the quantum case. And finally, so this is, if you want to actually find this alpha h bar, so finding alpha h bar is what is we do find this quantum Birkhoff normal form, then you can do this because, or you can do this essentially by introducing some constraints on what the alpha h bar can be, and you do this as follows. So going to be choosing near each critical value, I'm going to be choosing a basis of flat sections. One of those flat sections is the vanishing cycle. One of them is something that just intersects the vanishing cycle, and everything else doesn't intersect the vanishing cycle. So in this basis, the Gauss-Modin connection, which this vector bundle E is equipped with, has this very simple form that you can write down with a nilpotent connection matrix. And essentially, you can try to write down, using this, you can try to write down some constraints on the section alpha h bar. So you choose a global basis. The bundle E is actually trivial because everything is on a line. So you can trivialize it by choosing a basis. In the basis, you can write it down with some components, S1 to S2G. And now you want to determine these component functions by placing some constraints on them. So the idea is that if the correct alpha h bar satisfies these constraints, and there's only one possible section that satisfies these constraints, then the section that satisfies the constraints is the correct one. So and here they are, essentially more or less rewritten using change of basis from the global trivialization to the trivialization locally in terms of this basis of flat sections. Then if you do that, you can write down these conditions on the component functions. So you can see that S2 is essentially going to be this important component of the canonical one form. And you can see this third condition, 3, is actually quite interesting because it involves the digamma function that I had up earlier. So the condition is that essentially some sort of singular part of something involving these first two component functions is always going to be given in terms of this digamma function written in terms of the canonical coordinate. So these are the constraints that are actually satisfied by the real canonical one form, but unfortunately just specifying these constraints is not enough to uniquely determine a section of this bundle E. So we've computed this out for just a simple example where it's a cubic Hamiltonian, like y squared is equal to something cubic in x. And even in this case, it's the constraints written on the previous page aren't enough. So in order to have a sufficient number of constraints, you need to also introduce some restrictions on how the functions S1 to S2G behave near infinity. So that means there has to be an infinity, which there currently isn't because everything is on a line. So to add in infinity, you want everything to be over CP1. So you introduce a partial compactification of the symplectic surface by adding in a fiber at infinity. and then extending this vector bundle in connection to the corresponding projective line. And so now the conjecture, which sort of verified in at least this cubic example, cubic Hamiltonian example, is that the behavior of these functions near infinity is given in this way, where if you write down the corresponding power series so that the coefficients end up being power series in H bar, you actually get their polynomial, so that they cut off somewhere. And if you add this constraint together with the previous constraints, that should be enough to determine a section of the bundle E, and also that this should be something that the correct canonical one form satisfies. So that should determine it uniquely. So that is essentially what or one of the things that we're doing now. Right. So I ran over time a little bit. Should I stop, or I have like just under 5 minutes?
You can go the time. It's
okay.
Not a problem.
Okay.
Okay.
Yeah. So I have a few more things to say, and I mean this is just further questions or further directions to take this. And so, of course, a lot of the things I talked about in this talk are true even in the case where n is greater than 1. So in the n equals 1 case, I have just the surface mapping to the line, and there's only one function h in 2 variables. But if I have h as a function in multiple variables, then a lot of this other stuff works. So the Birkhoff normal form, as I've stated it, in terms of these various commutative diagrams, exists in the multivariable case. And the part between the correspondence, or about the correspondence between deformations and quantizations for this integrable system without the critical points still works. That still works. But the part that involves this vector bundle E, placing constraints on the sections and these variations of Hodge structure, that part is sort of not entirely clear. So that's something to work on. And of course, you can also try to look at non-Morse critical points, so something more complicated. And hopefully in that case, there are also normal forms that you can quantize. And then another thing that should have been discussing more recently is also, so we've been using this correspondence between deformations and quantizations to construct this canonical one form, but maybe it's possible to do away with that. So we want to be able to take integrals in this non-commutative algebra setting, and one way of doing that involves this Alan Kahn's non-commutative geometry. And so here you have some sort of quantum. In our case, it's going to be this non-commutative quantum algebra functions, and the role of the forms that we're integrating is going to be played by periodic cyclic homology for that algebra. And then the role of cycles is going to be played by these Fredholm modules. And so you can somehow try to define these non-commutative periods or this non-commutative canonical one form directly without going through formal deformations.
But for that, you need some analysis, it's not just a formal thing, because this Fredholm module,
so in the n equals 1 case, at least, maybe it's possible to just keep the do the cohomology class part of it and not quantize the cycles at all. So it might be possible to simplify it and not have to worry about the Fredholm modules and the analysis.
Okay.
But yeah, I mean, in general, it probably need to do something else. And I mean, finally, just one last thing is that, again, this is going back to this result of Sjöström's and connecting it back up to computing spectra of Hamiltonians, quantum Hamiltonians. Maybe instead of doing it through these results involving analysis, you can compute some sort of algebraic version of the spectrum, define the spectrum of quantum Hamiltonian purely algebraically. And there's also some ideas. Maxim has some ideas about doing that in terms of something similar to looking at D modules. So that is, I think, everything I have to say. So thank you.
Yeah, thank you very much. Very interesting talk. So questions? So basically you have like, if you have an integrable system, you have a fine structure on the base near a non-degenerate point, and you can kind of quantize it, which means replace functions in the neighborhood of the fiber by some non-commutative algebra, and you can embed these affine coordinates on the base into this non-commutative algebra, and you extend this to the simplest possible, to the sort of A1 Cadeira singular, to the Morse yeah, it's quite interesting. Which means, yeah, all right. And you are dealing with the neighborhood of a point. You do not consider a neighborhood of the whole critical fiber, which is a little bit strange.
Yeah, it's just the point.
Yeah, all right. Now, since you mentioned it's in your one of the last slides, that you can generalize to, at least it's a problem, one possible generalize to Hamiltonians with non-Morse critical points. So I just imagine the simplest symplectic surface, which is a C square, yeah, and some like in the style of the Milner's book, yeah, I take some maybe algebraic function with a unique critical point. Yeah, so there is a corresponding knot, which is intersection of the curve H equal constant with a three-dimensional sphere. So can you potentially write down some new algebraic knot invariants, like computing the spectrum of this quantized non-Morse Hamiltonian? Will it be?
I mean, currently I don't really know, but it would be definitely something interesting to look into.
Yeah, so it's quite a lot of a lot of questions, not enough time. Yeah, also there was this like 40, I think, yeah, exactly 40 years ago, paper by Witten on supersymmetric quantum mechanics and Morse theory. And I remember something similar. I mean, it's C infinity, it's not holomorphic, but nevertheless, he considered Hamiltonians with the potential UV, and this V has, I believe, a Morse critical point, and he wrote down some asymptotic expansions for eigenvalues. And then I think he interpreted Morse inequalities in terms of this type of data. It was kind of a starting point for many things. Actually, in a sense, mirror symmetry grew up from this toy model example. Yeah, but yeah. Is there any relation to this kind of Witten's? Because you also
there should be, yeah. I mean there should be, but again, yeah, everything that at least we've done has sort of been this kind of local local thing around like one point rather than combining them together.
Yeah. He has like if your function has several Morse critical points near each of them, you can construct, according to him, some approximate eigenfunctions. I think Leung recently, maybe not very recently, 5 years time framework, he reconsidered that old paper by Witten. Yeah, he construct near each critical point some approximate basis of eigen functions, and the whole whatever Hilbert space is a direct sum of these spaces. Each comes from the its own critical point, and what you are doing somehow resembles that thing, because in the end he also has some global object and global spectrum of operator here, and you have this variation of Hodge structures.
Yeah, I
and
mean,
you take,
I mean, I don't know, because the normal form kind of part of it is global, but the actual spectrum computations, even in this like sort of weird algebraic interpretation, is all local. So I'm not sure.
Also, it's interesting because he used this type of things to write down in a different way to interpret the Morse complex of the function. Yeah, in holomorphic setting, the Morse complex is trivial because all critical points have the same Morse index. But there is this wall crossing story, how different critical points interact. Yeah, okay, too many questions. Yeah, maybe let's give a chance to other people to ask something. Okay, are there any questions from?
Yes,
Okay.
You two can talk a little more at the other part, so give me a chance.
Okay, go ahead, Zonjo.
Okay, Sasha, have you thought of just this Birkhoff normal form or the quantization in the quiver setting?
In the quiver setting, how?
If you, for example, you just do the double quiver and you have a C and you have a double quiver, you have automatically you have a symplectic structure on it.
I'm in doubt whether they are Morse. I mean,
it depends on what the Morse function you want to take.
Yeah, so indeed, yeah, it's interesting. Yeah, there are many integrable systems coming from quivers, but
yeah.
I think that they have more complicated behavior near the discriminant. Like Hitchin system have quite complicated behavior near kind of, if you go deeper to discriminant, not just to the smooth locus of the discriminant divisor.
And also in your last question at the very end, you were thinking of using the D modules because of the deformation depends on the H. If you specialize H, of course, you will do here under the completion. When H equals 1, that is exactly the algebra's completion of the var algebras, this algebra of differential operators. And I was also kind of thinking of Birkhoff's normal form, because here the Morse theory, the H is at this point is it's a critical point, so it has to be smooth. But sometimes I don't want to have some 1 over z to a finite power, not all the way to the infinite, with some kind of a singularity.
Mm.
Does that make any sense of this kind of deformation theory?
Sorry, are you asking about looking at instead of formal power series, you're looking at like some sort of Laurent?
Yeah, Birkhoff also has something, but decomposing some functions which has singularity as a product of 2 parts. One part is smooth and the other part is singular.
Yeah. Yeah, I mean, we haven't actually considered it, but
Yeah, actually, it resembles something which we did, which we are doing with Maxim. It's like, imagine that you consider a Higgs bundles with a Higgs field which is meromorphic itself. So, but then the way how we handle this story, we replace the surface, the original symplectic surface, like a tangent bundle to a curve, for example, to a projective curve, we replaced by another one by making blow-ups. So on the final surface, your function is no longer singular in the finite part, but it's singular on some compactifying divisors. And then it's slightly different geometry, because I understand that Sasha spoke about symplectic surface, and here you have, maybe I'm wrong, but, and there we had the Poisson surface. Yeah. Yeah, it's interesting. Yeah, but in the end we have, again, we have something non-singular, some non-singular map, for example, in his framework, but from the Poisson surface with certain behavior at the complement to the open symplectic leaf. Yeah.
I mean, yeah, we also had a sort of, when we tried to do this example in this cubic Hamiltonian and try to sort of compactify everything, you end up with something that ends up with poles at infinity. But it was like something very, very simple, and I don't think we really even.
No, I think what Zonju means that you have singularities of your classical Hamiltonian not only at infinity, like for cubic Hamiltonian or whatever, any polynomial, but at the finite point as well.
Yes.
Yeah, no, I mean, I understand. I just, yeah, I don't know, unfortunately.
Yeah, but that's, yeah, it's a reasonable question. Yeah. But when you start to quantize, so it's kind of, it's what he was explaining, it's completely unexplored area, because it's not clear how to quantize it. So there are people who are doing some sort of Poisson geometry, describe some singular behavior of Poisson structure, or maybe functions on the Poisson, because you're basically classifying, you have some group acting on germs of functions, and you want to classify to describe the orbits. It's like Jordan normal form in the simplest possible example. But in the quantum case, I'm not surprised that there is quantum Birkhoff normal force. Yeah, so it's interesting. Yeah, all right. More questions? Well, if there are no more questions, so thank you very much. Very interesting talk, and too many questions to ask. All right, thank you. And so then this is it for today.
Thank you.